DFS and BFS are not the same. These have been considered two twin brothers of graph algorithms, and yet this is not true. DFS is better and it's not even close. Before we get into the reasoning, let's get some context. As you may know, there are these things called graphs. Essentially, they represent some kind of network. Graphs are composed of nodes and edges. A good example would be this. Nodes are cities and edges are roads between the cities. Or nodes might represent people and edges friendship between people. There are a lot of variations of graphs, but at their core they represent some network. But they are tricky to work with. See, the lack of rigid structure is problematic. It makes them more powerful than, say, an array, but you have to be more powerful too if you want to handle them. For example, let's take a look at this problem. We have a street with houses on it, numbered 1 to n. Now we want to find a distance between two houses. With a linear street it's trivial. Get the position of the first house, second house, and find the difference. But if we now say that we have not a linear street but, say, a neighborhood where there are some roads between houses, this problem suddenly becomes way trickier. For example, in this case, we can clearly see that the distance is 3, but how would you find it algorithmically in a graph that looks like this? Most work on graphs can be done with breadth first search and depth first search, commonly referred to as BFS and DFS. As you could probably tell by the name, these two are quite similar, both search or traverse the graph, usually all the nodes. The only difference between the two is the order. BFS starts in a node. It then visits all the neighbors of this node in any order. After that it visits neighbors of neighbors and so on. Note that we visit each node only once, we don't want infinite loops. DFS also starts with a single node. Then, instead of visiting all neighbors, it picks just one. Now that it's in a new node, it visits a neighbor of that node, and so on. It does that until it runs out of unvisited neighbors. When that happens, it returns to the previous node, commonly referred to as its parent. From here, it tries to visit more nodes and the cycle repeats. Eventually, we iterate through all the nodes and return to the starting node, where we end the search. Let's implement this real quick. Both are really simple since essentially there are 4 loops but 4 graphs. We'll store a graph like this, an array of vectors. These are C++ lists. The way it works is that for each node we keep a list of all of its neighbors, so G1 here will consist of 0 and 2. Here's a quick code on how you can input such a graph. Now to do BFS, create a bool array visited of size n to mark visited nodes, and a queue of nodes. Put s into queue since that's where we'll start. Now let's iterate on nodes in a queue while we have any. Take the first node with queue front and remove it from the queue with queue pop. Now iterate through all neighbors ignoring visited ones. Here, add this neighbor to the queue with queue.push. What we also want to do is mark this neighbor as visited. Even though we didn't visit this node yet, we want to prevent adding it to the queue twice. For example, here. Also mark the starting node as visited for the same reason. And with that, BFS is done. For DFS, all we have to do is simply replace a queue with a stack. That's it, that's how similar these are. Now you might think the utility is on the same level too, but as I already said in the start of the video, that's not so. DFS is better. But how? One reason is that DFS and BFS solve a lot of the same problems. But what makes DFS better is the implementation. See, the way we did before is by creating a stack of nodes and iterating through all of the nodes, one by one. Same with BFS, just replace stack with queue. But there's a much cleaner way to write DFS. It's this. If you are confused, don't worry. We create a recursive function. What happens when you call it? We first mark this node as visited, so that we don't visit it over and over again. Then we go through all of its neighbors. If a neighbor has been visited, we skip it. Otherwise, we call DFS on it. Now what happens is, in the first function call where node is 0, we wait for this new function to complete. This means that this loop gets stuck until the second function call completes. Now do the same thing but in a different node. Mark as visited and iterate through all of the neighbors. That first node had already been marked as visited, so we will go to all other nodes in this branch. Wouldn't it just infinitely loop? Well, we visit nodes only once, so we will run out of nodes eventually. Here's an example of when that happens. You can see that this node obviously got a bunch of neighbors, but all of them had been visited. This means that this for loop exits and the function returns. Now we go from a parent again. If there are any unvisited nodes, go there. If not, return. But hold on, how is this even DFS? In our first implementation we created a stack. Here we just execute a function a bunch of times. See, the way the programming languages handle function calls is with a stack. When you call the function, nothing after that call executes until the function is complete. So a CPU or whatever appends this function call to the stack, runs it until it returns, and only then removes it from the stack. It is also called popping from the stack. This way programming language doesn't continue unless it has calculated the result. That's how we can implement DFS without creating a single stack, just by using how function calls work. Well, great, what about BFS? And that's the problem. There's no cleaner way to do this than what we've already done. And if you are solving a problem where it doesn't matter if you use DFS or BFS, then why bother? Why not just use DFS? The implementation is too good. Now, frankly, a lot of problems cannot be solved with either one. One of the most popular problems solved by BFS, but not vice versa, is that problem with houses. It's often referred to as shortest path. BFS can solve this problem easily. All we have to do is keep distances from a starting node and that's it. Create array distance of size n, assign distance of s equal to 0, since that's where the starting node is. Now here assign distance of neighbor equal to distance of node plus 1, because here we walk from the node to the neighbor. Because BFS first visits all the nodes closer to it, the moment we reach the target node, we know its distance. In fact, we can't reach any node in an unoptimal way. If you try an example where a shorter path to a node exists, it is clear that BFS would just follow this path. DFS, on the other hand, would probably miss the target and go into some kind of rabbit hole before inevitably stumbling upon the target node. And even then, when it does reach it, we still don't know the distance. We just know how many steps DFS took to reach it, but there's no guarantee that that's the shortest path. In this part of the video I wanted to give more examples of BFS problems, but frankly I don't know any. Every BFS problem I know simply boils down to shortest path. Dijkstra algorithm is just BFS but with a priority queue instead of regular one. A star is just Dijkstra but we sort the priority queue in a somewhat better way. Every row leads to shortest path. Please enlighten me with more BFS problems in the comments, I'd be happy to see those. DFS, on the other hand, is used everywhere. Because of how simple it is to write, it is most often used to traverse graphs. For example, connected components. And its special property, how it only leaves branches when they are completely traversed, makes it perfect to find cycles, topologically sort the graph, or work with trees. For example, calculating a size of a subtree. So many things are DFS, I find it hard to say what is not DFS. Depth first search is king. If you like this kind of videos, let us know with a like or a comment. We would like to explore more topics related to graphs, algorithms and programming in general. Feel free to suggest a topic that you would like to see in future videos. Thank you for watching and goodbye.